Hi everyone. Today I am going to explain chapter 2 section 2, which is about the Newton's first law of motion. But before starting to explain the Newton's first law of motion, I am going to explain the difference between external force and the net external force. Remember in the previous section we defined the force as interaction of an object with its environment. External force is in fact it's a force again, but this force will be applied on an object's interaction with the environment. As you see, there are this picture, this diagram is showing the free body diagram of a car. There are four forces acting on the car, which means this car is in interaction between its with its environment by four ways. One of them is force of gravity, which is due to the interaction of the car with the earth. Second one is force ground on the car. I mean, there's interaction between the car and the ground. Third one is the car is in interaction with the air, and then this air also applies a force on the car. Fourth one is the forward force acting on the car. Car is in interaction with the rod, and then the rod is pushing the car forward. All these forces are an external force acting on the car by its environment. That external force, an external force acting on the car by its environment, is a single force. It's just a single force that acts on an object as a result of interaction between the object and its environment. But net external force is vector addition of these forces, the sum of all these external forces acting on this car. So the sum of all the external forces acting on this car is called the net external force, which means I'm going to add them in vectors because force is a vector quantity. And the vector sum of all these four forces acting on the car is known as the net external force, the net external force, or other name, resultant force. Then if I represent net external force acting on this car, I have to add these four forces by vectors, just like this. F net external force, is equal to force of gravity in vector, force applied by the ground on the car by vector in vector, force of air resistance applied on the car by again in vector, force applied by the rod on the car in vector. So vector addition of all these forces will give us the net external force acting on the car. In fact, we are converting somehow, we are calculating or we are drawing just single force, a single force equivalent to the effect of all these four forces. Net external force means this. And we are going to now solve a few problems about how to calculate the net external force. Because force is a vector quantity, we are going to use vector addition method we'll learn in previous chapters for calculating the net external torque acting on an object. First question is, a gust of wind blows an apple from a tree. As the apple falls, the gravitational force on the apple is 2.24 Newton downward. And the force of the wind on the apple is 1.05 Newton to the right. Find the magnitude and direction of the net external force on the apple. So there are steps in the solution of a problem. First step in here, we should draw the free body diagram of the apple for the apple. So remember, free body diagram in the previous section we talk about this. First you have to draw a simple model of the object. It's an apple. So you can draw a circle, but I just in here put an apple. You are going to locate the apple into from its central mass to a coordinate system, xy coordinate system. And in here, in this question, directions are given up, down, right, and left. So I'm going to indicate directions right, left, up, and down. Next step is, let's draw the forces. A free body diagram means draw the force acting on the apple. The first force is gravitational force, which is because of the due to the interaction of apple with the earth. So its direction is downward. Gravitational force represented by Fg, and we are going to remember draw all the forces from the center of mass of the object. Second force is force of the wind applied to the right. So I'm going to draw a vector from the center of mass to the right and represent this force of wind by Fw. These are two forces according to question acting on this apple, and this is the Freiberg diagram for apple. Next step is use the vector addition to find the net external force. Remember, we are going to add these forces in vectors. We learned in previous chapters how to add the vectors, how to find the resultant of a vector. So I'm going to use head to tail method in here. First, I'm going to locate one vector. First, I will locate force applied by the wind on the apple, which is to the right, which is 1.05 Newton in magnitude. And I'm going to add second vector, which is the Fg downward to the tip of the first vector. Its magnitude is 2.25 Newton. And then resultant vector, which is the net external force acting on the apple, will be from the tail of the first vector to the tip of the last vector. This is the resultant vector or net external force acting on the apple. Then next step is to calculate the magnitude. To calculate the magnitude of this net external force, I'm going to use Pythagorean theorem. It's a right angle triangle, and in right angle triangle, one leg is perpendicular leg is the force applied by the wind. Second perpendicular leg is the force applied by the by Earth, which is gravitational force, and hypotenuse is the net force acting on the object, acting on the apple. So then I can use the Pythagorean, which is equal to inside the root force applied by the wind squared plus gravitational force squared square root. When I insert the numbers into the equation, I can get the magnitude of the net external force acting on the apple as 2.48 Newton. And questions asking find the magnitude and direction of the net external force. I will find direction as well. So I will calculate the angle the net external force doing with the horizontal. This angle I am going to calculate. We can use one of the equation of the right angle triangle. You can use the equation for sine theta, you can use equation for cosine theta, or you can use equation for tangent theta. I will use tangent theta. Tangent theta is opposite divided by adjacent. Opposite leg is Fg. Adjacent leg of this angle is Fw, which is the force by the wind. So then, if I divide them, I am going to get the tangent of theta. After that, I'm going to shift button of the calculator and then press tangent theta. Write 2.05. I will get the angle as 65 degrees. Then this 65 degrees is the angle between the net force or resultant net external force and the horizontal direction. So then I'm going to say that the net external force is directed 65 degrees below the horizontal line or below the horizontal. This is the solution of the practice problem 2. And another problem, question number 3, problem number 3 in practice again. The wind exerts a force of 452 Newton north on a sailboat, while the water exerts a force of 325 Newton west on the sailboat. Find the magnitude and direction of net force on the sailboat. Again, first I will start drawing the Freiberg diagram. Draw the Freiberg diagram for the sailboat. I'm going to draw a simple picture for the sailboat. And then I'm going to locate the center of the sailboat to the center origin of the XY coordinate system. Then I'm going to start drawing the forces. The first force is wind exerts a force of 452 Newton to the north. So directions are north is upward up to the page. So this down, east to the right, west to the left. I draw it like this. Then wind is going to push this sailboat in the direction of the north. I'm going to draw a vector from the center of the mass to in the direction of north. And this vector's unit is this vector's magnitude is 452 newtons. While the water exerts a force of 325 Newton west on the sailboat. So then I'm going to draw second vector, second force. Again, I'm going to draw it from the center of the mass of the sailboat to the west. Left is the west in here. So this is the force applied by the water exerted on the sailboat. Find the magnitude and direction of the net force on the sailboat. So I'm going to use, of course, vector addition to calculate the net force. Use the vector addition to find net force. I know that net force means vector addition of these two forces. Again, I'm going to use the head-to-tail method. I will locate first vector F wind, which is 452 Newton. Then I'm going to add second vector to the tip of the first vector, which is F water, to the west and to the left, 325 Newton. And then I'm going to draw the resultant vector, which is the net external force acting on the sailboat. And if I check this, I will see that this is again right angle triangle. I can use Pythagorean method to find the magnitude of the external force because two perpendicular legs are known. F wind is known, F water is known. I am going to calculate the hypotenuse, which is equal to the magnitude of the net external force. Let's use the Pythagorean. F net is equal to root of F wind squared plus F water squared. Insert the magnitude of both wind and then water's force into the equation. I'm going to get the F net as 557 newtons. Then I got the magnitude. Next step is calculate the direction. Again, I'm going to use one of the equation of sine theta or cosine theta. I will calculate this theta and I can use sine theta, cosine theta, tangent theta. Tangent theta is more useful, more easier than the others. Sometimes you can calculate tangent theta without knowing the hypotenuse. It's easier and more practical. Tangent theta is equal to opposite leg of the right angle triangle divided by adjacent leg of the right angle triangle. Opposite leg is F water divided by adjacent leg is F wind. F water is 325 Newton. F wind is 442. Tangent theta is equal to 0.72. After that, you are going to use your calculator. Shift tangent theta, right 0.72. Right answer, you are going to get the angle as 36 degrees. Then I can say that net external torque makes an angle of 36 degrees with north because that direction is north. So the next external torque is directed 36 degrees west of north. And then I will solve a simple problem. Karzan leaves his physics book on top of a drafting table that is inclined at a 35 degrees angle. The external force acting on the book is shown in the figure. Find the net external force acting on the book. This diagram is given. This is the free body diagram, in fact. These three forces. One of them is gravitational force, 22 Newton. Other one is the force by the inclined plane on the book, 18. Third one is the friction force between two surfaces, 11 Newton, and parallel to the inclined plane. Steps are again the same. First, you are going to draw the free body diagram. It's already drawn, but you should locate this object into the book, into coordinate system. Draw the free body diagram. As I said, it's drawn. It's given in the question. Second, represent x-axis. Locate the book into xy coordinate system. Represent x-axis in the direction of acceleration. This is important. So while we are drawing the x-axis, always use the direction of the acceleration, in which direction this object speeds up. This object speeds up along the surface, along a line parallel to the surface of the inclined plane. And then draw y-axis perpendicular to x-axis. So this is the coordinate system which I am going to draw, as you see. So x-axis is representing this, or in the same direction of the acceleration of the object. In this direction, object will accelerate. Y is going to be perpendicular to x. And according to coordinate system, if this coordinate system, two forces are along x and y axis, but one force is inclined. So Fg is inclined according to this x and y axis. That's why I have to resolve Fg into components. So to resolve a vector into components, you have to know the angle between this force and one of the axes. So you need to know this angle or that angle. So I have to calculate it. I'm going to use a simple mathematical rule. Just draw extend FG down, and if you draw a vertical line down, you are going to see that because this is horizontal line, and FG always perpendicular, vertical, that's why this angle is going to be 90 degrees. If this angle is 90 degrees, then I can easily calculate what is the angle between the gravitational force and x-axis, this angle. Because for a right angle triangle or just a triangle, the sum of the internal angles of the triangle is 180 degrees. Because this is 90, which means sum of 35 and that angle must be equal to 90. So which angle, which is going to be 90 minus 35, I can calculate that this angle is 55 degrees. So if I got an angle between the gravitational force and one of the axes, yes, I got it, I can resolve Fg into components. Then I'm going to draw the components. Draw a parallel line to the y-axis, perpendicular to x. This is going to be x component of Fg. Draw a line parallel to x-axis, perpendicular to y-axis. So this purple line is going to be y component of Fg. Then I can calculate x component and y component. If you look at that, 55 degrees, x component is adjacent side of 55 degrees, adjacent perpendicular leg. And adjacent one is calculated by hypotenuse, which is Fg, multiplied by cosine of 55. If I multiply Fg by cosine of 55, I can calculate Fgx. Fgx is equal to, according to this calculation, 22 is the Fg, multiplied by cosine 55, which is 13 newtons. And now let me calculate the y component. Y component is, as you see, which is Fgy, which is the opposite leg of the right angle triangle according to this angle, 55 degrees. So it will be calculated by hypotenuse multiplied by sine of 55. So Fg is equal to sine of 55, which is 22 multiplied by sine 55, which is equal to 18 newtons. Now I resolved this inclined vector to x and y components. Now I am ready for applying the vector addition, because I want to find the net external force acting on the object, which is sum of all these three forces acting on the book, which is F, force of friction, Ff, force applied by the inclined plane on the book, Fn, force applied by the earth on the book, Fg. So when I add them in vectors, I will calculate the net external force acting on the book. But one of the forces inclined, so that's why I'm going to first calculate the x component of the net external force by adding the x component of all these forces. And I'm going to find y component of F net by adding the y component of all these forces. Find the net force in both ends, x and y directions first. This is what I am talking about. So the x component of the net external torque will be equal to x component of friction force plus x component of the force applied by the inclined plane on the book plus x component of the gravitational force on the book by the earth. But while I am writing, if the force is in positive x direction, I should write them into this equation positive. But if the forces are in negative x direction, I should write them into this equation negative. In the same way, I am going to write the y components. Y component of the net external force is going to be equal to y component of the force of friction plus y component of the normal force plus y component of the gravitational force. Again, if the force is in positive y direction, I am going to write its value into the equation as positive. If the force is in negative y direction, I am going to write the value of this force into this equation as negative. Let's start. Look at Ffx. Ffx is along y-axis itself, but it's in negative y direction. That's why I'm going to write this equation negative 11. F and x. If a vector is along y-axis, it has zero component. That's why x component of Fn is 0. It's on y. If a vector is along y-axis, its x component always 0. But Fgx, if you look at the direction, you are going to say Fgx is in positive x direction. That's why I have to write Fgx as positive 13 into this equation. So let's write it. Negative 11 plus 0 plus 13. So result is going to be plus 2 newtons. This plus indicates that the x component of the net force must be in positive x direction. So then I'm going to draw x component of the net force on this diagram. So let me draw the diagram in here again. So x component of the net force will be in positive x direction. I am going to draw a vector along positive x direction. Let me do the same thing for the y component for the net force. F5, because friction force is on x-axis, its y component is going to be 0 this time. So if a force is along x-axis, its y component is 0. F and y, if I look at the picture diagram, I see that Fn is itself along y-axis. And because it's in positive y direction, I am going to write it as positive 18 into the equation. Fgy, if I check the diagram, I will see that Fgy is in negative y direction. So I'm going to write Ffy 0, Fny positive 18 because it's positive y direction, but Fgy negative 18 because it's in negative y direction. So when I add them, I am going to get the result as 0, which means this net external force has no y component. The net external force has no y component. In this case, if there is no y component, only x component exists, which means net force must be equal to its x component. So thus the net external force F net will be equal to only the x component, its x component F net x. Then I'm going to write that net force magnitude is equal to F net x magnitude, which is equal to 2 Newton in positive x direction, parallel to the inclined plane.